Boom, welcome back. So in the former class, we were discussing pH. Now we're going to look at buffer solutions. Yeah, buffer solutions. After buffer solutions, we're going to talk about KSP. After KSP, we're going to talk about common ion effect. And thereafter, we discuss precipitation. Now, what is a buffer solution? Let me just give you a pure, simple history of how buffer solutions came into play. First, it is important for you to know that no substance on Earth can retain its pH when exposed to the atmosphere for a long period of time. If I take pure water, as pure as water is, if I expose water to the atmosphere, just give it a period of an hour or two, it will either turn to a basic solution or an acidic solution. It will lose its pH to either 7.1, 7.2, or to either 6.8, 6.7. Now, the big question is, it was just exposed to the atmosphere. What happened? Simple. Atmospheric oxygen or the atmosphere comprises of carbon dioxide and silicate materials. When carbon dioxide comes in contact with pure water, it forms a weak acid, which is triazocarbonate 4. Weak acid, and that makes the pure water to be slightly acidic. If carbon dioxide doesn't act on it, then silicate materials in the atmosphere, which are basic, will act on it to make it more basic, and you have a pH of about 7.1, 7.2. Silicate materials are purely micas or fluorspars or quartz. These are minerals you find on the Earth crust. So when they come in contact with them, they increase the base of the pure water solution, hence making the pure water solution to be basic. Now, because of this inability of a substance to retain its pH for a long period of time, the concept of buffer solution came into play. The big question scientists asked was, what can we do to retain the pH of a solution when it is exposed to the atmosphere? So that when a little amount of acid or even a little amount of base is added to it, it is resistant to change. What can we do to a solution that will make it resistant to pH? That is how the concept of buffer solution came into play. And from research, a combination of a weak acid and its conjugate base, in brackets salt, gives you a buffer solution. And that buffer solution can resist change in pH. For example, ethanoic acid and sodium ethanoate. If you have that combined and put into a solution, that solution will definitely be resistant to pH. And because you are making use of a weak acid and its conjugate salt or a conjugate base, is called an acid buffer. Now, if however you decide to make use of a weak base and its conjugate acid, which is salt, then you have what we call a basic buffer. For example, I have ammonia mixed together with ammonium chloride. That will give me a basic buffer, right? So there are two basic types of buffer, acidic buffers, basic buffer, but you can see a third one called a salt buffer. We're going to talk about that later. Example of acidic buffers are a combination of hydrofluoric acid and sodium fluoride, hydrocyanic acid and potassium cyanide, ethanoic acid and sodium ethanoate. These are acid buffers, while basic buffers are ammonia and ammonium chloride. And then you also talk about ammonium hydroxide and ammonium chloride. These are basic buffers. They are common basic buffers you will always hear and see. Now, that takes us to the facts. The facts as far as this concept of buffer solution is concerned. Number one, the resulting pH of a buffer solution. The resulting pH of a buffer solution, that is a solution that is made up of a weak acid or a weak base, together with this conjugate acid or conjugate base, also called salts, is given by the algebraic sum of the pKa plus the log ratio of the salt to the acid or base, as the case may be. For an acid buffer, the pH is simply the pKa plus the log of the salt, the concentration of the salt to that of the acid. For a basic buffer, the pH now for a basic buffer is actually called pOH, right? Not pH. For a basic buffer, the pOH is the pKb value plus the log ratio of the salt concentration to the base concentration to base 10, right? Now, pH can also be rewritten as, instead of using salt, you can use base for acid. So the pKa value plus the log ratio of the base concentration, which is the conjugate base concentration anyway, together to the ratio of the acid concentration to base 10. That gives you the pH of a buffer solution. That's the formula for the pH of a buffer solution. Now, this equation is actually called the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. Very, very important. You have to remember that at the back of your coconut. Very important. And then let's talk about the pH of a salt solution. The pH of a salt solution is a little bit peculiar. It is just the same way, just that there's a very slight difference. The pKa of a salt solution, the pH of a salt solution is simply half the pKw, that is the potential of pure water dissociation constant, plus pKa plus log C. So half in bracket pKw plus pKa plus log C, close your bracket. C there stands for the salt, right? That's the concentration of the salt. pKw is 10 raised to the power minus 14. Sorry, Kw is 10 raised to the power minus 14. So pKaw becomes minus log of 10 raised to the power minus 14. And then the pKa remains there. So by the time you substitute that correctly and solve, you will have a pH of a salt to be 7 plus half the pKa plus the log of the salt. And that gives you the pKa, or the pH of a salt buffer. All right, very important. So the only difference there is that it's more or less like the formula of an acid buffer, just that it is purely log to salt and 7 plus half of it. That's what we mean. So that takes us to the next factor, which is what happens when you now add a little amount of acid or a base in a buffer. What happens when you add a little amount of acid to a solution, a buffer solution? What happens is that the concentration of the acid will definitely increase, isn't it? I have a buffer solution that is made up of a weak acid and its conjugate base. I add more acid to it. It becomes more acidic. And what happens to the resulting pH? The pH will decrease because a lower pH value is an increase in acidity, right? Good. So all you need to do now is what will now become the new buffer equation, or the new pH of such buffer that has experienced an addition of an X molar concentration of an acid or an X molar concentration of a base. What becomes the new pH of such solution? Now for an acid buffer, the pH becomes the pKa plus the log ratio of the salt concentration minus the amount of acid you added in molar, which is X, all over the acid plus X concentration. So for the acid, you add X. For the salt, you subtract. Why? Because more acidic the buffer solution will be. Now, what will happen if it was a basic buffer that you are adding more base to? Of course, it becomes the pOH becomes the pKb plus the log ratio of the salt plus X. Yes, the salt will not be plus. No. The salt minus X divided by the base plus X, because you're adding more base. So what happens to such pH? Such pOH will actually increase in value, because the higher the value, the more the pOH, as the case may be. Now, have you ever thought of yourself adding X molar concentration of an acid in a basic buffer? Adding X molar concentration of an acid in a basic buffer. So what will become the new pK? What will become the new pH of such concentration? Since you are adding an acid to a basic buffer, the pOH becomes the pKb plus the log ratio of the salt plus X, because you are adding, sorry, I'm talking about adding an acid to a basic buffer, right? So it's pKb plus salt plus X divided by the base minus X, because you're adding an acid to a base. And you can always do that for the other way around. A typical exam question can come in play, and you are asked, what is the pH of a solution if 0.2 mole of HCl is added to 1 liter of a buffer made up of 1 molar concentration of ethanoic acid and sodium ethanoate? That's a very simple question. So you are adding 0.2 mole of HCl in 1 liter. So you have to first of all calculate the concentration of the HCl you are adding in that acid buffer. It's an acid buffer because it's ethanoic acid and sodium ethanoate. So we're talking about pH equals to pKa plus log ratio of salt minus X divided by acid plus X. Good. So the concentration you're going to get, which is 0.2 divided by the liter, which is 1 liter, that's 0.2 molar. Substitute it for X. Get your pKa value. If you're not given the pKa value of ethanoic acid, you got to know it, bro. There are some pKa values that you should never forget. In fact, they will not give you an exam. They believe that you're supposed to know. And those are the pKa values of ethanoic acid, pKa values of ammonia, and that of ammonium. They will not give you. You're expected to know them. As far as ethanoic acid is concerned, it has a pKa value of 4.7447. As for ammonia, because it is a base, it has a pKb value of 4.745. As for ammonium, it has a pKb value of 9.25. Those are pKb values and pKa. You're supposed to just know them. Remember, if you are given pKa and you are looking for pKb, just subtract from 14, isn't it? And that will give you the answer to the question you are asking for. So it is not that difficult to get. Yes. So that takes us to the next one, which is solubility product. Now, the solubility product of an aqueous solution in equilibrium is simply the product of their ionic concentration raised to the power of their individual number of moles, provided that the solute, which is always solid substance, is slightly insoluble in water or very insoluble in water. Now, this is usually equal to a constant called the solubility product constant, aka KSP. So the concentration, the product of the concentration of the product raised to the power of the number of moles is what we refer to as solubility product constant, KSP. And it is measured in mole square per dm cube raised to power 6, since it is a product of two different concentrations. And of course, if you are given HA, which is equal to in a reversible reaction in equilibrium, NH plus and MA minus. So the concentration of A raised to power M, the concentration of H raised to power N will give you their product will give you the KSP. So here you are expected to calculate the solubility of that substance that has dissociated. Let's say, for example, you are given calcium tetraoxophosphate, right? And you're expected to calculate the solubility of calcium tetraoxophosphate. The first thing you're going to do is to dissociate tetraoxophosphate. It will give you 3 moles of calcium ion and 2 moles of phosphate ion. Now, for you to get their KSP, it's going to be the concentration of calcium raised to power 3 times the concentration of sulfate raised to power 2. Now, having gotten to this stage, the next step you're going to take is let the solubility of calcium phosphate be X. And the solubility of this calcium phosphate will take the position of calcium and phosphate as a product of their number of moles. What do we mean? So you're going to have 3x raised to power 3 dot 2x raised to power 2. 3x for calcium because there are 3 moles of calcium. Then for the phosphate, it becomes 2x because there are 2 moles of phosphate ion. Then raised to the power of their same 2 as the case may be. So by the time you calculate that, you make x the subject of the formula, you are going to have the 5th root of the KSP divided by 36. That is that for a 3:2 concentration, or a 2:3 KSP. You can calculate 1:2 KSP, you can calculate 1:2 or 2:1 as the case may be, even 1:1 KSP. So 1:1 KSP is simply the square root of KSP. 1:2 KSP is the cube root of the KSP divided by 4. Then 2:3 KSP is the KSP divided by 36. That's the 5th root now. Then 3:2, stuff like that. You can always do the mathematics and get yourself settled. However, the bigger the KSP value of a solution, the stronger the solubility of that solution. What does that tell you? KSP is directly proportional to solubility. If the value of KSP is big, the solubility of that product is also going to be big. That's what we're saying, a direct proportionality. So that's that for solubility constant. So that takes us to common ion effect. Now, the concept of the common ion effect is an application of Le Chatelier's principle, which states that when the concentration of a particle in a substance is increased, that is in equilibrium, the equilibrium position will shift in a direction so as to accommodate the new or foreign material introduced. Now, the common ion effect is simply a phenomenon that describes the solubility of a solute in a solution that decreases as a result of the addition of a common ion to the solution. What do we mean? I have a solution of sodium chloride and I'm adding hydrogen chloride. The common ion here is chlorine, right? So because I am adding hydrogen chloride in a solution of sodium chloride, the concentration of hydrogen fluoride will increase. Hydrogen chloride will increase. Why? Because more of the chlorine ion will be formed at the product, which will eventually favor the backward reaction. And of course, the hydrogen chloride is actually in quote insoluble. So because it is insoluble, it will produce more of the insoluble precipitates, which at the end of the day will decrease the solubility of that substance. Let me give you another example with another element. Let's say, for example, silver iodide. We know it's an insoluble substance, right? On dissociation, we give you silver ion and iodine ion. Iodine ion, silver ion are the dissociation values of silver iodide. And now pour silver iodide in a container containing potassium iodide. Take note, the common ion here is iodine. Now, by the time I do such, the concentration of iodine will increase, which is at the product. Now, increase in the concentration of the product will definitely favor the direction of lower number of moles, which is the reactant. So it will favor the production of more silver iodide. And because more silver iodide will be produced, which is already insoluble, will definitely decrease the solubility of the solution. You get it? So the decrease in solubility of a substance on addition of an element or a compound having a common ion is called common ion effect. I hope that's perfectly clear. All right, so let's give you a typical example. For example, you are given you're asked to calculate the solubility of silver iodide in 0.1 molar of potassium iodide at 25 degrees Celsius, taking the KSP of silver iodide to be 8.5 times 10 raised to the power minus 17 mole square per dm raised to the power 6. First, you write the dissociation equation, which is silver iodide. In irreversible reactions, you have silver ion and you have iodine ion. Then you draw your table. Your table should be divided into three components. You have the initial concentration of the potassium iodide, which is the initial concentration of the substance that is receiving what you're adding. Then the second one is the change in the concentration. And then the last one is what happens at equilibrium. And you have to arrange them directly under each of the products of that silver iodide. So for initial concentration of ions in potassium iodide, first there was no silver iodide. There was no silver ion, so it's 0. Secondly, the iodine ion before adding silver iodide is 0.1. Yeah. Why is it 0.1? Because potassium iodide on dissociation will give you potassium and iodine. And if the concentration of potassium iodide is 0.1, therefore iodine is also 0.1. If probably iodine had a coefficient of 2, that means 2i, then you multiply that by 2. So it's a very sensitive topic. Next is the change in concentration. Now, on adding silver iodide to the solution, what is the concentration of silver ion? You can call it X. X molar of silver ion was added, and then X molar of what? Of iodine ion was also added to the solution. Now, why is it XX? Simply because silver iodide is a 1:1 compound. If it was a 1:2 compound, you will now have X molar of silver ion and maybe 2 molar, 2X of what? Iodine. If it is a 2:3, it will simply be X and then 3 times. You get the point. So you have to be very careful because these are very sensitive things never to forget. Then what happens at equilibrium? At equilibrium, you sum the two of them. 0 plus x, that's x, then 0.1 plus x will give you 0.1 plus x. Now, take note, because the value of x is infinitesimal, a very little amount of iodine will dissolve in the solution. So you refer to that x as being equal to 0. So it is approximately 0.1. So you now write the new equation. That's now the new KSP of the solution of potassium of silver iodide in potassium iodide. It will now be the product of x molar raised to power 1 and then 0.1 plus x, which I've already assumed to be 0 anyway, as 0.1 raised to power 1. Why it's going to be raised to power 1 is because silver iodide is a 1-to-1 compound. And then once you do that, you can equate it to the KSP. Your KSP value is given to you as 8.5 times 10 raised to power minus 17. And then make x the subject of the formula, and boom, you get the solubility of silver iodide in potassium iodide. Now, the solubility of silver iodide here will drop because the value of x you have is 8.5 times 10 raised to power minus 16. Meanwhile, the initial KSP given to you is 8.5 times 10 raised to power minus 17. Now, the big question is, how did it drop? Does it not look like it has increased? No, it has not increased. X is solubility. KSP is the product of two solubilities. So if you really want to get the KSP of the new silver iodide in potassium iodide, all you need to do is to simply multiply that new solubility times 2. And that will give you about 7.2 times 10 raised to power minus 33. So that is a new KSP. And by so doing, you will discover that the KSP value has actually decreased. And because there is decrease, that simply means that common ion effect has taken place, right? Now the question can be asked in another dimension. You can be given, instead of KSP, what if you are given Ka instead of KSP, or Kb instead of KSP? How do you calculate the solubility of a substance with common ion to another? That's what we're about to do right away. So, for example, if you are given 0.5 molar concentration of hydrofluoric acid mixed with 0.1 molar of sodium fluoride, and you're asked to calculate the solubility of hydrofluoric acid, given that the Ka value of hydrofluoric acid is 6.8 times 10 raised to power minus 4. Now, if you check, you are given concentrations of both. You are given the concentration of hydrofluoric acid that is added, and you are also given the concentration of the receiving solvent, which is sodium fluoride, to be 0.1. And you are given Ka value to be 6.8 times 10 raised to power 4. Now, the first thing to do is to write the dissociation of the acid. Of course, dissociation of an acid must have water, so as to produce hydrozonium ion and the conjugate base, which is normal, okay? So the water must be there. So don't ask where the water is coming from. So you have hydrofluoric acid plus water will give you hydrozonium ion plus fluorine minus. Now, you write your table, draw your table, initial, change in concentration, and at equilibrium as usual. Now, the only difference here is that you are going to include the product and the reactants to the table. You are going to include the concentration of the product and the concentration of the reactant to the table. So, hydrofluoric acid will have its column, water will have its column, hydrozonium will have its column, and then hydrogen fluoride will have its, and then fluorine ion will have its column. So, on the column of hydrofluoric acid, first, the concentration before you add it to sodium fluoride, hydrofluoric acid was initially 0.5, water was 0, ammonium was 0, hydrozonium was 0, while fluorine was 0.1. Why is fluorine 0.1? Because that is the concentration of the receiver, which is sodium fluoride, right? Good. Now here, under change in concentration, you now have X molar of hydrofluoric acid. So minus X. As for the water, is dash. The concentration of water will not change throughout the table. And then as for the hydrozonium part, you will have plus X molar, and then on the hydrofluoric part, plus X molar as well. Remember, if the ratio of the compound was 1:2, then you will have 2X molar for fluorine. Then at equilibrium, you add up. The first column for hydrofluoric acid will be 0.5 minus X. Water will have no effect. The other one will be 0 plus X. The other one will be 0.1 plus X. So you have gotten their various concentrations at equilibrium. So the next thing to do is to draw your Ka at equilibrium of that new concentration at equilibrium. So Ka becomes the concentration of hydrozonium times the concentration of iodine of fluorine all over the concentration of hydrofluoric all over the times the concentration of water. Now, because water did not change from the beginning to the end, the concentration is 1. And then as for that of hydrozonium, we have already assumed it to be X. That of hydrofluoric is 0.1 plus X, but the X is assumed to be 0, so it's 0.1. Then that of hydrofluoric, you will have it as 0.5 minus X. Then solve the value of X, and boom, you have the solubility of hydrofluoric acid in sodium fluoride. Take note, the common ion is fluorine. All right, so very quickly, we take the last part of this chapter. This is already very long, and that's precipitation. Given a particular reaction, or let me say a particular substance in equilibrium, cadmium sulfide, for example, to give you cadmium ion plus sulfide ion, the product of their two concentration will give you KSP, right? Good. If the product of their two concentration happens to be less than the KSP of the solution, then you refer to it as being unsaturated. If the product of these two concentration is greater than the KSP, you say it is a supersaturated solution. If, however, the product of these two concentration is equal to the KSP of the solution, then you refer to it as a saturated solution. That's the first fact under precipitation reaction. Then the last fact on precipitation reaction is the speed of precipitation of a substance is inversely proportional to the KSP value of that substance. You get it? So the higher the KSP value, the lower the speed. The smaller the KSP value, the faster the speed of precipitation. So in most cases, you can be given two substances in a vessel, and you're asked which one will be precipitated first. The first thing you need to do is calculate the values of their KSP. The one that has a small KSP value will be precipitated first because it will be fast, while the one that has a higher KSP value will be precipitated last, right? So basically, that is that for that. And that is the end of this chapter. And we thank God that we're able to conclude it. The time is quite long, and it's raining right now. All right. Thank you for your time. God bless you. And let's see you in the next chapter. Boom.